Afternoon, nerds. A couple of you got it back. That's nice. Thank you. Alrighty, so like I said, today is the inaugural video for Algebra 2 Honors Notes, and we're going to start with section 1.1 and 1.2. And the reason why I put these things together is because there was some stuff that I skipped because it's not standard, or there just really wasn't enough for me to justify calling it a whole section. I hate busy work, so if I can cut things out, I will, because I don't think they're important. And don't worry, if I say it's not important, you're not losing out on any knowledge at all. I promise. We do need to start talking about some vocabulary, though. I know that your copies don't look as nice as mine. I did save the nicest copy for the end of the day for the recording. So earlier in the day, they looked at an ugly copy under the camera like you guys have in front of you. I saved the nice one for you, so it's easy for you to read it up there. And also, it's better for the YouTube, link down in the description to the merch and the bio and all that stuff. Anyway, so definitions. A relation describes the relationship between two sets that are usually represented as ordered pairs, inputs, outputs. And since this is an algebra class, x comma y, where x's are the inputs, y's are the outputs. More on that in just a second. A function, which hopefully you're all very familiar with the terminology functions from Algebra 1, is a rule, usually an equation, named f of x, f for function. But it could be anything, could be p of x, m of x, h of x, whatever we want. And it literally just says, oh, we've got an equation here and x are the inputs, and it's a function. It defines a relationship between one variable, the independent x, another variable, the dependent, usually y. More specifically, though, what makes something a function is that for every x, there's exactly one y. And you could say that a function maps x values onto y values. That's really more of an upper level mathematics thing like college math. You don't have to worry about that. The set of all input values is called the domain. So our x values are our domain, whereas our y values are the range. So domain is x's inputs, range is y's outputs. And if you have the graph to look at, and not just an equation, then you can use the vertical line test, hopefully you remember this from Algebra 1, to determine if something is a function. Basically, if a vertical line can touch your graph in more than one place, vertical, by the way, is up and down, then it fails. The vertical line test is not a function. Cool? This should all be old material. Here's a very abstract representation of some relations. We have x's in this blob and y's in this blob. Same thing going on over here. X's are the domain, y's are the range. And here's what we have. Every one of these x's, x1, 2, 3, and 4, they all have a single arrow leaving them. They all point to a y value. So every x points to one y value. None of these x's points to two y values. Therefore, we have a function on our hands here. But Mr. M, there's two arrows pointed at this y value. I'm aware. That just means there are two different x's that can get us the same output. Let me put it in terms that maybe you're more comfortable with, calculators. If I grab this calculator and don't have graphs to look at, if I grab this calculator and I say, 5 plus 3, how many different answers can it give me? 1. You know why? Because plus is a function. Addition is a function in mathematics. So this one input can only return one output. And it doesn't matter how many times I type 5 plus 3. I'm going to get the exact same output every single time because addition is a function. But the y values are not unique, are they? There's a different input. Same y value. But addition is still a function because no matter how many times I input 1 plus 7, I will get the same output every single time. So hopefully that helps clear up what it means to be a function, why outputs can repeat, but inputs will never give two different outputs. Could you imagine if you grabbed your calculator and you type 5 plus 3 and you're rolling the dice because you don't know which of two answers it was going to give you? Sounds scary, doesn't it? Kind of trust these things to be accurate all the time. Now over here, this is not a function. And the reason why is because one of my x's has two different arrows that leave it. We have an input that somehow or another gives you back two different outputs. This one x could give us this output or this output. Once again, 2 arrows point here. Is that an issue? No. What it is an issue is having 2 arrows leave 1 output. Now, I'm never going to test you on abstract math like this. It's just a picture representation of what it means to say maps onto. Cool? Okay, a couple people nodded, so we're just going to go with cool. Before we try to answer this question, I want you to understand what you're looking at. These are images of graphing calculator screens. Notice there are no numbers on them. So they look like that. It's a graphing calculator screen. And since they have no numbers on them, we have these intervals for the x's, intervals for the y's, to show us exactly how big this window is. And that's what we call it. It's a window. It says my x-axis starts at negative 4.7, ends at positive 4.7. My y-axis at the bottom is negative 3.3, and at the top is positive 3.3. And all 3 windows are exactly the same size. I just wanted you to know that that's what those images mean. Now we get to talk about the pictures on those graphs. I'll be looking for a class answer, okay? And I'll be looking for yes or no, and I'll prompt you when I say, okay, class, things like that. I say, based on what you see, class, yes or no, is this a function?
Yes.
Okay, so most people say yes, and I'm going to have to agree, and here's why. If I let this pencil represent a vertical line, so straight up and down, I can't find a single place on here where this pencil would have hit this graph 2 different times. So for every x that I draw a vertical line through, a single y value is returned. So we're going to go with yes, this does pass the vertical line test. The second one, class, yes or no? Is this a function?
Yes.
Yes, it is. I see, again, I could draw any vertical line I want to through any x I want to, and it's only going to hit this graph a single time. So every one of those x's maps onto a single y. And lastly, this last one, class, yes or no? Is this a function?
No.
Of course not. Obviously, if you looked at the directions, it says which is not a function. So we knew one of them wasn't going to work, right? But no, this is not a function. This fails the vertical line test, and I'm too lazy to write all that out. So I'm going to say I can't. Vertical line test, VLT. There we go. And just to prove a point, I'm going to draw a single vertical line that hits this graph more than once. There's a lot of them, but I'm just going to draw one. Right there at x equals 1, I can see at least one place where a single x value can give me different y values. In fact, this can give me 3 different y values. It can give me a y value that's a little bit bigger than 2, a y value between 0 and negative 1, and a y value just before negative 2. So big time no-no. Easy peasy, right? Okay. You have homework questions like that. It's just like yes or no with these functions. And you just click yes or no. Now this one down here, this is an image that I made on Desmos. If you guys are hopefully familiar with Desmos, Desmos.com, graphing calculator stuff. Great program. I love it. I use it a lot in my notes to try to make images so that they're good examples. The one that was in the book from your textbook was, so I made up a better example. For this thing, what we're going to do is we're going to identify our domain and our range. So what are the x's and what are the y's? And then we're going to answer some input-output questions about it as well. However, to make it a better example that goes along with the homework even better, I do need you to edit one little thing. Down here, instead of having this be a solid dot, let's make it an open dot. To the best of our abilities, okay? I'm going to pretend it was at perfectly -2, -3. Just going to make it an open dot down there, not closed. This one's closed, the other one's not. Cool? Difference between open and closed. A closed dot means this is where this thing stops, but it also includes this value. An open dot means this is where this stuff stops, but it doesn't include this number. This number is the barrier, but it doesn't count. Everything infinitely close to it does count, but it itself does not. All right. So domain and range, throughout the years, I've realized that it's tricky for students. When they look at a graph, they're not quite sure what it is they're trying to find. The domain of a graph, the easiest way that I can describe it is what x values does it cover up. Imagine that the graph can cast shadows. I have a light up above and cast shadows straight down. I want to know what x values would have a shadow on them. Or if I put the light below it and the light goes up, what x values would end up with a shadow on them. Another way you could say it is, imagine you had the ability to squish these things flat onto the x-axis without it squeezing out of the sides. What x values are covered up? That is what it means when you say the domain of a graph. So I'm looking for a brave volunteer because I'm trying to learn names, looking for hands, and I'll call on people as I go to try to help me figure out what the domain of this is. Who can help me out? And don't worry, the microphone can't pick up your voice very easily. What's your name? Ilya. Tell me, what do you think the domain is, or where do you think the domain begins?
At 1.
And when you say 1, are you talking about an x value, a y value?
Y1.
Okay, so remember, when we're talking about domains, we're talking about the x's only. So imagine there is no, you're not off the hook yet. Imagine there's no up or down. There is only left and right. You're going to squish this thing flat onto the x-axis. Tell me, what x does it begin with?
-2.
Begins at -2. Does it include -2?
No.
It does not. And where does this domain end?
At 9.
At 9. Does it include 9?
Yes.
Yes, it does. Cool. So we're talking about a domain between -2 and 9. Don't include -2. Do include 9. Thank you, Ilya. Appreciate you. How do we represent that, though, is the question. We could use inequalities. I don't want to use inequalities. What we want to stick with, for the most part, is interval notation, using brackets and parentheses. Don't worry, I'm going to teach you in case you've never seen it or heard of it. I'll write this answer in inequalities because it's important that you understand how they relate to intervals. So he says between -2 and 9, don't include the -2. Here's how that looks. -2 is less than x, which is less than or equal to 9. But we're going to try to use interval notation only. And the way this works is we use a parenthesis on a number if it's not included, like -2. We use a bracket on a number if it is included, like +9. The domain would be listed like this. From -2, without including it, up to 9, and include it. I know that looks kind of like a weird coordinate. I'm aware. But since the domain of a function can't be a single point, it can't be an x comma y since domains are only x's, this is how you describe all the numbers between -2 and +9, including +9. That's how you would describe that. Are you comfortable with that idea? Some words on interval notation. From left to right, your numbers will always be written from small to big, just like they would have been for a compound inequality like that. They're always going to go from small to big. Don't include, parentheses. Do include, brackets. There it is. And just to really drive home what's going on in the picture, I'll do this. Imagine the whole x-axis was shaded from there to there. That would tell you those are all the x's that would have shadows on them, but we wouldn't be able to include -2. Now the range is the same trick, but instead of casting shadows onto my x-axis, I'm casting shadows onto my y-axis. So help me out with range. What's your name? Daniel. Sir, if you don't mind, in interval notation, what do you think the range is?
In inequality or?
Just in intervals. What's the smallest range value?
-3.
Do I include it?
No.
So bracket or parenthesis on the -3? Parenthesis because it's not included. Good. And where's the range going to stop?
5.5.
5.5. And does that get a bracket or a parenthesis?
Bracket.
Bracket because it's included. Perfect. There we go. Thank you so much. Daniel. And Ilya's over there. Just trying to names, you know. There it is. Domain. Oh, I should probably put my stuff on the y-axis. Domain and range using interval notation. You can imagine the whole y-axis would be shaded between those two marks. The y-axis is like a vertical number line. Questions, comments, concerns on interval notation before we go on to input-output questions? Yes, sir. What's your name?
Jake.
Jake.
What's the, I thought you said that we're not doing inequality.
So I only wrote the inequality so that you can see what it looks like when you write it in interval notation. Because I'm just trying to get you to see that
Those two mean the exact same thing?
this statement and this statement, yes, mean exactly the same thing.
So
This is inequality notation. This is interval notation.
So, like, whatever, like, ask us to, like, so if we type in 1 or 2, then we've gotten it, right?
Well, the questions will typically say answer in, so they'll tell you how to answer.
And what's the bottom one called?
This is called interval notation. This is what we will stick with. Don't worry, you're going to see it a lot. Interval notation. The homework has mostly interval notation. I did choose one question because I liked the question, but the answer does say an inequality, so you'll use inequality. There's another way of writing spans of numbers called set builder notation. I skipped it. I didn't even bother introducing it to you guys because it's not standard for the state of Florida. And to be real with you, I never used any set builder stuff until I was in like junior, senior level math classes in college. Classes that most people will never see. It's very useful in extreme upper level, but not at this level. It's just not useful. It seems redundant and stupid. Okay, the next 4 questions are all about input outputs. Remember, f of x is a fancy way of saying a y value. If I had given you an equation, and then I said find f of -1 with an equation, who could tell me what I was asking them to do? If I say find f of -1, I give you an equation, I say find f of -1. What is that telling you to do? What's your name?
Brody.
Brody, what's it tell you to do if you have an equation?
Telling you to set the x as the number in parentheses.
Exactly. I'm replacing the x's, I'm substituting with the number that's in the parentheses. So if I gave you an equation, I said find f of -1, you understand that the thing inside the parentheses was an x value. It says x is -1, what is f of -1? That means what is the output going to be? What is the y value when x is -1? Thank you, Brody. So could someone else, because I'm trying to learn these names, tell me at x equals -1, what is my output value on this graph? And it's okay to estimate because I know it's not perfect. So take yourself to x equals, Parker, right?
Is it -1?
So at x equals -1, it's close. It's really darn close, yeah. Let's color code this thing. At x equals -1, it's close to -1. We could say it's about -1 if you want to. We'll just make the dot fat and go, yeah, that was a perfect point. So we'll say it's about -1. Don't worry, you won't have to say it's about in the homework. They're exact graphs. I wanted to pick a piece of spaghetti for this question, but the ones in the books are like straight lines and things like that, so it's a lot more obvious. Good, thank you, Parker. How about f of 1? Looking for new volunteers, trying to memorize those names. Daniel? Daniel, what is f of 1?
1.
It's 1 tick mark, but look at the scale again.
Wait.
When x is 1,
What?
what number does it line up with on the y-axis?
1. Wait. 0. Wait.
So look, at x equals 1, look at the y value.
Isn't that 0?
0.5.
Wait. Where?
Right here?
I was looking at 0.5.
Yeah, I think what happened was the fact that the x-axis goes by ones, but the y-axis doesn't, threw you off. But yeah, so we're looking right there. At this x equals 1, our y value is going to be 0.5. That was exact. Appreciate you. So for these last two, they say find an x so that f of x equals a number. Remember what f of x means. F of x means y values. So we got our y-axis here. So for these last two questions, what we're doing is we're asking ourselves, if y was that number, what x could have got me there? Just give me 1, because there's probably more than 1. Still looking for names, new volunteers. What's your name?
Barry.
Barry, could you please tell me 1x that gives us f of x, equals 4. 6 feels good to me. If I could find a pen color I haven't used. I haven't used a lot of blue. So f of x being 4, we can track it over from the y-axis and see that, yep, it tracks down perfectly to x equals 6. That's not the only answer. It's also like 6.8 or something like that. But we only needed one answer. So we've got x equals 6 will get us there. And then the last one, just looking for one more volunteer for, and I believe this one has to estimate as well. Looking for an x value that will return the y value of 1.25. And what's your name? Jake. Haven't you already helped me, Jake?
No, I asked it.
You asked a question. Okay, Jake. See, I should have known. All right, Jake, what do you got for me? It's okay to estimate it.
1.5.
Yeah, it's like 1.5-ish, 1.75-ish, something like that. This 1.25 is, let's go with 1.75. Again, on the homework, you don't have to stress. They're going to be exact. They're not spaghetti graphs like this one. All right. So inputs, outputs, domains, and ranges from a graph. When we flip this over, we start to get to some stuff that I find is often difficult for students, and that is, what if you didn't have the graph? What if you have no clue what the graph looks like? Just by looking at the equation, can you still find the domain? You see how I haven't asked you to find the range? Most of the time when you're asked to find a range, it's either from a very well-known graph of what it looks like, or you would just grab a graphing calculator and graph it and then say, what's the range? You really don't try to find the range by hand in mathematics. But domain we can do. So let's talk about what it means when you're saying domain once again. It means the x values the graph covers, but it also means the x values that you were allowed to plug in. Earlier, I can't remember who it was, but somebody told me when it says f of -1, that means plug in -1. What was your name? Brody told us. So he knows that this means this is an x he can plug in. When we have an equation, though, we have to talk about the kind of x's that can be plugged into certain things. There are certain things that are not allowed underneath a square root bar. Is there somebody that can tell me what they remember is not allowed underneath the square root bar, even on a calculator? You try on a calculator and it goes, fork, and it just doesn't work. What can't be under a square root bar, Brock?
Negative numbers.
Negative numbers. Negative numbers cannot be underneath square root bars. Does that mean x can't be negative numbers? No, that's not what that means. It means the stuff underneath the square root bar can't be a negative number. And I'll use the very technical term, stuff. There is a name for the thing underneath the square root bar. It's called the radicand. And more specifically, you could say it is the argument of the radical. We're just going to say the stuff underneath the square root bar. Stuff under square roots can't be negative. So what can it be if it can't be negative? It can be positive. What else can it be? This has been tripping people up all day. What else can it be? What's your name? Thomas, what else can it be? Well, it can be a fraction, but that fraction is probably positive, right? What else can it be? Decimal, that's just a fraction again. It's probably positive. I know I've just asked you twice what your name is. Brody, I'm so sorry. I'm going to get there. It can be 0. You can take the square root of 0. It's 0. So that's an easy one. So it can't be negative. It can be 0 and it can be positive. So what we do to figure out the domain of a square root function is we take the stuff that's underneath this square root bar and we say that stuff can be greater than or it could be equal to 0. That will guarantee not negative. Now what we do is we solve for x, and when you solve for that x, you have found the domain of the function. You're going to subtract a 2 from both sides, and it's going to give you, and I know I'm using inequalities to solve this, but I will write the domain in interval notation. It'll give us that our domain is x is greater than or equal to -2. That means all the numbers greater than and including -2. So as an interval, this domain begins at and includes -2. But how do I describe all the numbers on a number line that are bigger than that? Infinity. Because if you go to the far right, you will be reaching towards positive infinity. I can't draw infinity symbols, so I draw double O or double zero, whatever you want to call it. They always look like squished fish when I try to draw an infinity. It doesn't work. Ready for a mind bomb? Infinity is not a number. You can't reach it. You'll never get there. It's a goal. It's trying. But because it's not a number, it cannot be included. No infinity, positive or negative, can have a bracket on it. It's not allowed. This describes to all mathematicians all the numbers beginning at and then bigger than -2. Cool. Someone earlier asked me to clarify and just explain it one more time. Are we all comfortable with why I said x plus 2 would be greater than or equal to 0? Okay, just making sure. Part B, my function, is now a fraction. Fractions have a single rule that you are never allowed to break. And to help clue somebody into what that rule is, I will remind you that fraction bar means divide by. So anybody that thinks they remember a new person, preferably, so I can try to learn more names, because I've called on Brody like 30 times today, and I'm just now going to know his name. I'm trying to get all these names. Who thinks they know the one rule about fractions? Now, you just told me your name, but I forgot. What's your name? Thomas. I'm so sorry, Thomas. What do you think is the one rule? You meaning when you say can't divide fraction, what do you mean?
Like you can't divide the whole fraction. It's like both denominator and also numerator.
Oh, say you're talking about can't have fractions in places of the fraction.
Yeah.
You can, it's just not pretty. And you probably don't, a lot of people probably don't remember, when you say divide by fraction, do you remember maybe a teacher telling you like keep, change, flip, or keep, flip, change, something like that? That's what we do when we divide by a fraction. So we don't want to leave them like that, but it can be done. I'm talking about there's one thing that you can't do with a fraction, not even on a calculator, where you try and it just goes, no. Sebastian, you can't divide by 0. That's the one big no-no with fractions. Can 0 be on the top of a fraction? Yeah, all day long. Then the fraction equals 0. No worries. But we don't know the size of 0. We don't know how many zeros can fit into something else. So because of that, we can say that you never have 0 on the bottom of a fraction. Does that mean x can't be 0? No. X can be whatever x is. What you can't have happen is the bottom can't equal 0. Again, I know I should be very technical here and use better words than bottom, denominator, but the bottom cannot be equal to 0. So when you're trying to figure out your domain of a fractional function, you take the bottom and then you say this cannot be 0, and then you solve for x, and that will tell you the no-no for x. So we add 5 to both sides, and we get that x cannot be positive 5. It could be any other number except for positive 5. Imagine you had a number line and everything was shaded except for 5. On that number line, if everything was shaded, what would we see at that 5, if you remember your number line graphing? What would we see there? If I say you can't include 5, an open circle. What are we using to represent open circles in our interval notations? Parentheses. So how do I make sure I have parentheses at the 5, but I get all the numbers smaller than 5 and also all the numbers bigger than 5? Literally what happens is the 5 breaks the number line into 2 different sections. And we have to list out both sections. We have to say all the numbers to the left of 5 and then going all the way up to 5. But don't include it. How would I describe all the numbers to the left of 5? Infinity, but infinity is to the right. So what's to the far left?
Less than
Well,
negative.
negative infinity. There we go. So yes, it is an infinity, but it's negative. Once again, infinities are not numbers, so you can't bracket them. Negative infinity is the smallest thing imaginable. Anytime you have to write it in an interval, it will be written first. Positive infinity is the largest thing imaginable. If you have to write it in an interval, it will be written second. So then the other side of the number line is begin at 5, but don't count it, and go forever up to positive infinity. In mathematics, there's a symbol we use that says, oh, and also this stuff. It's called a union symbol. It's also called a cup in mathematics, but it means all of the numbers to the left of 5, but don't include 5. Oh, but also all the numbers to the right of 5, but don't include 5. It's like, I like to say it hops over the number with a union. You get to hop over it with a union. We only use unions when they have absolutely nothing in common. There are no numbers in this set that are also in this set. Okay. And then the last one for today, this says a of x, some function a of x is equal to 4x squared. Now let's pretend there was no words here. If I said what's the domain of this, once again we're talking about things you're allowed to do. Can anybody think of any number that they couldn't raise to the second power, where you'd try and the calculator would tell you no? Or could you put in anything you want and raise it to the second power?
Zero.
Well, if I raise 0 to the second power, this means 0 times 0, right? What's it going to give me? 0. So if that was the only one that was coming to mind for anybody, what that tells us is I can raise any number I want to the second power. So the domain should be all real numbers, right? Negative infinity to positive infinity. But a of x is the area of a square, and x is the length of the side of the square. So think of any shape you want. There is one thing you guarantee for every single shape that you know about the length of its side. It's so obvious that I've been having trouble getting people to say it today. What do we know about the length of any side of any shape? Megan? It can't be negative, and it can't be 0, so it's guaranteed to be positive. So the length of any side of any shape is guaranteed to be positive. That means these x's had better just be strictly greater than 0. But as an interval, we said strictly greater than 0, which means do not include it. Just like that. Because it's a real-world problem. And I think that that's a good spot for us to stop, nerds. Thank you so much for the very first Algebra 2 Honors video on my YouTube channel. I appreciate you. You've gone down in history.